Happy day, everyone. You are welcome to Orekoya Olusegun Physics Mathematics Fundamentals on YouTube channel. Today's topic is on physics. We are going to discuss the concept of electric charge, electric field, electric field intensity E, the electric force F, and the electric potential V. Before we go into all these topics, please don't forget to like, share, and make comments on my video. Also, please kindly subscribe to my YouTube. Thank you so much. Now, we are going to the concept of electric charge. Now, before we do that, we talk about we need to discuss something about atom. That is a very tiny part of every matter. Now, an atom is said to be electrically neutral in the sense that the total number of protons in the nucleus of the atom counterbalance the total number of electrons that is revolving around the atom. This arrangement is like a planetary body. Inside the nucleus, we have what is called neutron and proton, and what is moving around them is this electron. Electron is very light compared to proton. Now, electron carries what is called negative charge, and proton carry what is called positive charge. Neutron does not carry any charge. So, because electron is very light, it can be easily lost or can be easily gained by the atom. Now, if an atom loses electron, it's no longer called atom. It is called ion. If it is loss of electron, the next charge on this ion will be positive, and this particular positive ion is called cation. Now, if this atom gains electron, if it gains electron, the next charge on that atom will be negative, and this negative ion is called an ion. Now, what is electric charge? Electric charge is the state of the particle of a matter that determines how it will behave when it is placed in an electric field and a magnetic field. The combination of electric field and magnetic field is what is known as electromagnetic field. Now, when we have this ion that is charged, and when we have this ion also that is charged, each of them is called a charge. And then, according to the fundamental law of electricity, like charges attract. Like, for instance, let me say I have charge Q, which is positive, and I have charge Q, which is also positive, or I have charge Q, which is negative, and I have charge Q, which is negative. These charges, because they carry the same sign, they will repel each other. They will repel each other. These charges, because they carry the same charge, they will also repel each other. So the first fundamental law of electricity is that like charges repel. But if this charge carry positive and this charge carry negative, they will attract each other. So the law says that like charges repel, unlike charges attract. So we should get that at the back of our mind. Now, what is electric charge again? Electric charge is the property of a matter that determines how it will behave when it is placed in an electromagnetic field. Now, what is electric field? Let me say I have this charge and it is positively charged. The forces, the line of forces coming from this charge is outward for the positive charge. This line of forces. If this charge is negative, the line of forces is going inward. The line of forces will be going inward. So this space around this charge, where the influence of the electric charge can be felt is known as the electric field. Now, if this particular electric field is acting on a particular charge called test charge, this test charge will experience electric force. If this test charge is positive, you can see if this one is positive, this particular two, they are like charges, they will repel. So this test charge will move away from this particular charge when placed in that field. Now, we talk about electric field intensity. Electric field intensity E. Electric field intensity E is this force. This force acting, pushing this thing away per that charge. That means electric force per unit charge is known as electric field intensity. It's given us the idea of the amount of force acting on a test charge when this test charge is placed in an electric field. So electric field intensity E is given as F over Q. So by cross multiplication, we have electric force to be electric field intensity times the test charge Q. This is the equation 1 for the electric force. Now, we have what is called Coulomb square law. We have what is called Coulomb's square law, inverse law. We call it Coulomb's Coulomb's inverse square law. What is it talking about? It's talking about the same electric force F. He said that this electric force F is directly proportional to the product of the source charge Q and test charge Q divided by the square of their separating distance. When we remove this force proportionality sign, we have F is equal to K QQ divided by R squared. What is it saying is this: when we have a source charge is the charge that we assume is creating electric field that is to be acted on a test charge placed in that field. This is a test charge. So this test charge is experiencing the electric field around this charge. So the electric field is the influence around the electric charge, where the test charge will experience a force acting on it. Now, this force F is acting on this test charge at Q, and the distance between them is this R. So according to Coulomb's square law, it's saying that this force F acting on this test charge Q due to the electric field created by this source charge capital Q is given as the product of the two charges QQ divided by the square of their separating distance. So in a nutshell, my F is equal to KQQ divided by R squared, where K is given as 1 over 4 pi A naught. This A naught is called permittivity of free space. Free space. Now, I have two formulae for electric forces now: the Coulomb square law and the one that gives us the product between the electric field intensity and the test charge Q. So let's put these two expressions together. Since my F is also equal to KQQ divided by R squared, I can equate this together. So I have what I'm going to have now is EQ is equal to KQQ divided by R squared, and the Q on both sides of the equation cancel out. So my electric field intensity can also be written as KQ divided by R squared. That is a source charge divided by the distance of separation between these two charges. So I have two expressions for my electric field intensity now, E. So you can have this one as a formula for electric field intensity, which is force per unit charge, or we have it as a as being proportional to the source charge divided by square of the separating distance. Now, another concept we want to introduce is what is called electric potential. Potential. This electric potential is also similar to gravitational potential. Under electric potential, we are dealing with charges. Under gravitational potential, we are dealing with masses. Like for instance, let's say I have mass m at position p1 at a distance h from the ground level. We know that gravitational force F will be acting to take this mass from point P downward. So what am I trying to say is that at this point the potential energy of this mass PE is maximum. Maximum in the sense that the potential energy is given as a mass times gravity times height. Now, if this particular mass fall down to the ground level, my height will become 0, which means the potential energy becomes 0. In a nutshell, when a mass is falling down, the potential energy decreases. But if I leave this mass upward, I'll be acting against the direction of gravitational field. That means there is a work being done against gravitational field. In this case now, the potential energy will be becoming higher and higher because the height will be increasing. So as the mass is moving against the gravitational field, the potential energy increases. But when this mass is in the direction of the gravitational field, the potential energy decreases. The same thing is applicable to electric potential. Now, let's consider two charges, this positive charge and the negative charge here. The electric forces normally act from the positive charge towards the negative charge. If I have a test charge Q in this place, now if I want to move the test charge Q from this point to another point in the electric field, we can discuss rather I have to do a work against the electric field. So the electric potential V is the work done per unit charge when this unit charge is being moved from one point to another in an electric field intensity E. So in a nutshell, V is equal to W over Q. And then from metrics, we know that work done is force times distance, that is F times R divided by Q. So, and this F has two formulae. One of the formula that I said is F is equal to QE, and it's also, according to Coulomb's inverse law, is KQQ divided by R square. So I can use either of these to represent this F. Let me come first with using this force for the force. So instead of this F, I can have it as a QE times R divided by Q. This Q cancel Q. So in a nutshell, my V now, that is electric potential, is equal to E times R, that is ER. So electric potential V is E times R. Now, if instead of me using F is equal to QE, if I want to use this inverse square law of the Coulomb, I can have my F as KQQ divided by R square, then times R over Q times R divided by Q. This R cancel one of this R and the Q cancel Q. So I'm left with KQ divided by R. So my V is KQ divided by R. That is electric potential. Now, this particular electric potential, by definition, is the work done per unit charge in an electric field, or the work done in taking a unit charge from infinity to a particular point in an electric field. Thank you so much. This is Orekoya Fumi Olusegun, Physics Mathematics Fundamental on YouTube. I hope that you have gained one or two things in this class concerning the introduction to electricity. Please remember to subscribe to my YouTube, like and share. Thank you so much. Have a nice day. Bye.